I work for Intel, currently involved with the Zephyr project. I will be giving you an overview of the project, what we are doing, what we are planning to do, and some technical details about how things work in Zephyr. So basically, this is the agenda, and talking about starting with what is Zephyr. So, I mean, obviously, you came to this presentation, so you have some idea what I will be talking about. It's a microcontroller operating system, very small memory footprint, open source under Apache 2 license, and it's hosted by the Linux Foundation. The project was launched almost 2 months ago with Intel, NXP, and Synopsys as co-founding partners. It supports multiple architectures. So we support ARM, ARC, x86, and we are in negotiation and talking with others to integrate and also adding architectures as we go. So over time, we will see more architecture support and board support. So when looking, I mean, a lot of you will probably have this question: why are you doing it? Why are you releasing yet another project? Yeah. So we did some analysis, and we have been looking at the market over the last few years, and it is a very well saturated market. There's a lot of alternatives out there. When we started looking, we wanted something that is permissively licensed. So this already was a filter for a lot of operating system that didn't make the cut for us, because we are looking for a true open source code base. There are a lot of them out there that are research products or maintained by one person and so on. And these were very difficult to deal with and to start with as a common base for something that we hope will change the industry. And we wanted something that is focused on IoT. So just taking a kernel, a scheduler, would not have got that. We wanted actually more than just a scheduler. We wanted more than just a kernel. We wanted an OS. So basically, applying these filters, we came to the conclusion that we needed another OS there to actually satisfy most of these requirements that we had. So this is basically the why. It's a strategic investment. We are not trying to reinvent the wheel. So we're trying to look around and see what technologies are out there, what can we learn from what's available in other projects, and learn from the experience and the mistakes some of these projects had over the years. We wanted to have a true open source project. That's why we released that as part of the Linux Foundation. It's released by the Linux Foundation with the partners involved in creating this project. Permissively licensed, established code base. So, I mean, Zephyr is not something new. I mean, the code base is well established. It has been there for more than 15 years, went through a lot of commercial acquisitions and ended up in with Wind River, which then became Intel, and then we over the last few months we have been working on making this open source worthy and ready for open source release. And one of the main aspects we have been looking at is security. So we wanted to take this source code, the established source code that we had, and try to release something that is, and design something that is secure from the start. Security is the main aspect already now. We are looking at how we want to implement security features, do things in a secure way, comply with secure practices for developing code, and so on. So security is a major thing in the project. Of course, we will have security features as we go, which in most cases will be either stack related or hardware related. and we look into support all of these features that would be relevant for an IoT platform. So besides security, we are also looking into making the project more modular in a way that allows developers to pick and choose components as they see fit. So we don't want to lock anybody in by introducing inflexibility there. We want the project to be flexible. You should be able to build for the smallest of devices with the least removing all the functions and features that you don't need, and make it fit on things like 8K MCUs out there. But we also want to allow users to start moving up the stack and adding features as they need and as their products develop. Architecture support is very important, so we want to add support and enhance the existing support for architectures like ARM, x86, and ARC. And as I said earlier, add more architectures and introduce or make the project open for additional MCU and support from other vendors, which would help the project also deal with scalability and also deal with features that might be, for example, available on in one architecture but the other. So have something that is open for everybody in this case. Connectivity, we are talking about IoT, so connectivity is obviously a major part. So we have been working over the last year introducing a BLE stack, an IB stack as well. The BLE stack in Zephyr is something that we have designed and created from scratch. The IB stack is something that we took from an established project, the Contica project, and adopted for our needs. And we are building, or we are adding and putting the components together to create solutions for IoT installations and use cases by adding the protocols and the application layers on top of the stack to make it attractive, basically, for developers and users. The project, and this is actually why the project was released as an open source with a permissive license, is we want actually to have community involved as well. So the project is available for download. It was released in February. We are already seeing a lot of activity from developers, from people, sometimes hobbyists, but also commercial contributions from potential partners that are looking at the project in a serious way to integrate it in their products and to support their use cases and hardware. And this is something that happened really fast, and we expect to see more of that happening over the next year. So obviously, for an open source project, this means that the community will have a say, and community and you as community will be able to influence the project as it develops. And this is something which we see as very, very advantageous for the project. So talking about the project in details, so I took here, I listed the top 10 IoT technologies according to Gartner. This is a study that was released 2 months ago. And they are listing, obviously there are more details to the bullets here, but they are listing the top IoT technologies. Obviously security, analytics, being able to analyze data and send it for further analysis. Reading a sensor is one thing, but gathering data over days, years, months, and analyzing it is another thing. So it's actually a very important thing to deal with and to address in IoT devices. This is probably something that would not be happening on an MCU class system. This will be happening on the cloud, but the cloud is part of IoT in this case. Device management, very important, related to security. You need to be able, we are not talking about maker devices or like hobbyist projects. We are talking about IoT device installations in mass scale. We are talking about industrial installations of thousands or sometimes tens of thousands of devices, sensors, or whatever that need to be managed and in a central way and need to be updated if something happens, if there are security issues or whatever. So you need basically to be able to update, manage, and see what's happening in your network. And this also relates to the network and connectivity features of an IoT platform. Obviously, to be able to deploy such environments, you need low power, short range networks in some cases, but also wide area networks. And in most cases, this would be mesh networks that need to run over, on a coin cell for 5 to 10 years. So there are a lot of challenges there when it comes to power management and being able to connect and deploy these devices, update them, and manage them over time. So obviously, number 7 here, IoT operating systems. This is exactly what Zephyr is about. So it is the operating system technology is something that is very important. So you can't just create such an installation on an IoT environment or ecosystem without having the right OS and the right tools to deploy and use and build and develop this OS. And that's exactly where the Zephyr project comes and becomes very important. And that's exactly what we are trying to address with the Zephyr project. So going forward, this is a simplified architecture overview of what we are doing and what we are trying to achieve and what we are building or what we are aiming for with the modular design of Zephyr. So obviously, on a platform, you will have the normal default IOs that you would have on any IoT platform. Radios in some cases, or most cases today in modern MCUs. And then you will have a kernel. And you will see here 2 types of kernels. I will go into details about that a little bit later. But Zephyr actually operates in 2 modes. One is the nano kernel, and one is microkernel, which is a superset of the microkernel, a superset of the nano kernel. And the reason why we have 2 kernels here, we wanted to have a stripped down or like a minimal subset of the features Zephyr can provide to create a solution for systems that have memory limitation and constraint when it comes to footprint and flash and SRAM. And it's a configurable option in Zephyr. Right now, it's something that you can build a lot of the usage cases using the nano kernel. But if you need more, if you need networking, if you need complex multitasking, then probably you will be selecting the microkernel. So our goal in Zephyr, as I said before, is to provide an OS that runs based on MCUs for wearable and IoT devices. It needs to be highly configurable and highly modular. It's kernel mode only. That means you basically build your application, link it against a kernel, and generate one single static binary that you deploy on your device. There are no loadable modules. There is no runtime. And it's basically designed for simplicity and also to address or to be able to fit it on the smallest of devices. Everything is done, there's no user space. Everything is done statically and at compile time. So basically, you define your stack sizes, your configuration, the device drivers you want to use, and basically everything statically. So when you build your binary, you know exactly how much RAM, how much ROM you are going to consume, and you can basically control every aspect of the kernel at build time. So you don't leave things to you don't leave things for chance or when running on runtime. So architectures, I have said before, x86, ARM, ARC, and others under discussion. What we are trying to do so we have the IB stack and the protocols out there, trying to basically expose everything using a common API. So basically, when you write an application, the idea is that when you write an application for platform A, you should be able to build it for platform B without changing the code, and just basically run it exactly the same way and build it the same way. And we do that by having a common API for IOs and for networking. So never mind what is the implementation and what is the architecture beneath it. You are just talking one single API that is implementation agnostic. So what does that mean? I mean, when talking about different architectures, that we want basically to be able to support different frameworks that already exist to make it easier on developers to add support for new boards and new architectures. So we have right now, if you look at Zephyr, we have a lot of native drivers that have been written natively on Zephyr and for Zephyr using the Zephyr APIs. Some of these drivers would be for things that are not bound to a specific SoC. So talking about like sensors that you can plug on a board and things like that. So these are like native drivers that are not supported by any specific vendor of an SoC. However, when it comes to SoC and IOs, like I2C or GPIO, we want to be able to support them using the HAL frameworks provided by, for example, by Intel. This is the Quark microcontroller software interface, QMSI. For ARM platforms, this would be SIMSYS and the vendor-specific drivers that are supported for these platforms. And then, I mean, you can go further here by looking at Synopsys, for example. There's designware drivers already available in their open source project. So we want to support this as well. By doing this would make it basically easy for us to add new support for new platforms, but at the same time keep the APIs consistent. So these drivers have to be implemented in a way that does not change the APIs for the end user and for the applications. So when it comes to the IB stack, so this is a common, I mean, this is not necessarily Zephyr related, but that's basically where we are going. Yeah. So right now we have, let me go to the next one. This is basically the current status as we have it right now. So we have building things up. The Bluetooth is something that is originates from Zephyr. It was done for Zephyr. It's actually customized for Zephyr, supporting HCI, but also supporting some custom APIs available on the Intel Curie module, which is basically the Arduino 101 that you can purchase today. So we have the IPv6, UDP. We actually have plans to introduce TCP. And when I say here introduce, it's not something that we are going to develop from scratch. It's something that already exists in the Contiki project, and we are just going to enable that. We didn't enable that yet because we thought UDP and UDP is actually in this case is in IoT environment and installations is widely used and more attractive, especially when it comes to low power, low range, and even wide range networks. We have some drivers added for 15.4 for the Galileo, Ethernet on the Galileo, and all of that basically will go further, and we are looking at supporting Wi-Fi, NFC, as I said, TCP, and then adding the applications and the protocols on top of the IB stack to make useful things, basically, to send sensor data to the cloud, or to do device management using LWM2M and so forth. So when it comes to security, I mean, as I touched on earlier, I mean, there are features, security features that would come with the standards and IP protocols we are using, or network protocols we are using. So this is on the communication security side of things. But we are also looking at device security and supporting security features that come as part of a specific SoC or architecture. So for example, secure boot, trusted execution environments, hardware crypto engines, stack protections. This is something that has to be supported on the hardware. And we have to basically make sure that Zephyr runs in such environments, especially, for example, in a trusted execution environment. Zephyr would have to coexist or run in a VM-like environment and offload some of the secure functions or operations to a trusted environment. So Zephyr needs to be able to deal with these environments, yeah, and also with secure boot as well. Zephyr needs to be able to offload encryption to hardware where available. We need to enable and use stack protection features where available as well. And these are things that sometimes are easy to support and use because you basically just have to provide the hooks and the mechanism for the security environment to communicate with Zephyr. Most of these features will be implemented on the hardware, in the bootloader, and in other ways. We don't have to do much there, but we have to be aware that we are running in a secure environment. In terms of cryptographic libraries, some of you probably have seen the security session about Zephyr security session yesterday, but we have been working on adding optimized and footprint optimized, in this case, security backends to Zephyr to make the things like DTLS and TLS in general smaller in size. So footprint is a huge thing that we look at on a daily basis. We don't just let things slide in. We control what goes in, and we make sure that features are not increasing footprint without a good reason. So TinyCrypt comes here as a feature of Zephyr with an implementation of very common cryptography that can be used by things like DTLS or TLS or other mechanism that would be needed, for example, by Bluetooth and Wi-Fi and other protocols that need to communicate in a secure way. So as I said before, I mean, we are a static and a single binary application. We are basically a kernel-less, how do you call it? It's a library-based kernel. There's a single address space. There are no loadable modules. So with this feature, basically, we have eliminated a lot of issues that, I mean, surface of attack, if you want. And we have basically if something happens, if something is insecure, it's because whoever is actually created the kernel or put it on a device didn't do it right. It's not because of an external code that was loaded into the kernel, in a malicious way. In terms of planned security features, so device management, as I said before, we need to be able to update systems remotely. We need to be able to deploy features, new features, but also bug fixes to systems installed in a IoT environment. We need to be able to support to support multiple implementations of the crypto libraries and be able to offload cryptographic features to hardware where available. So that's where we will be basically adding APIs to abstract this type of functionality and make it easy for third parties or vendors to add their own implementation, whether software or hardware, to Zephyr. Secure key storage, another thing needed to support Bluetooth, Wi-Fi provisioning, and networking in general. We need to be able to store or at least we need to be able to do encryption using such secret keys in a very secure way. And that's where actually the trusted execution environment becomes very important. So you can actually do the encryption without exposing your keys to the OS and to the application, or even to the developer who's developing their application on the platform. So this was an overview. So now if we go a little bit deeper in the kernel, I mean, here I have a link to a video. I mean, if you go to YouTube, you will see the video that would actually, in 3 minutes, describe all the features and how the kernel works. I don't want to click on this right now because I'm not sure if it will work. Yeah, so you can probably search for Zephyr on YouTube. You will find this video. It's actually well done. 3 minutes gives you an overview of how the kernel works and the general architecture of the kernel. But now to get going, I'll talk a little bit more about what we have there in the kernel. So it's basically multi-threading. I mean, the kernel is multitasking kernel. I'm talking about the microkernel here. It includes both priority-based and non-preemptive fibers. So we have priority-based and cooperative scheduling. Interrupt services, including both compile time and runtime registration. We are actually leaning now towards supporting compile time, which is static interrupts only, which adds a lot to footprint and I mean, well, actually reduces the footprint and boot time and other advantages as well. Yeah. The code becomes deterministic, basically. We have, as on any other or many other OSs out there and RTOS kernels, we have inter-thread synchronization services, semaphores, mutexes, inter-thread data passing services, queues, events, and so on. Memory allocation. So basically, if your application requires dynamic allocation, this is available as well through linking with an external libc library, like newlib in this case, or using some of the services available to the microkernel, in this case, memory pools, where you can simulate the usage of malloc and you know, this is usually if you are just writing a small application, a self-contained application, you will not need that. You will be able to define the memory usage or memory used in a static way. However, if you want to link or integrate third-party libraries, like you know, you have an MQTT library that you want to use, or LWM2M implementation, or an HTTP client, or anything like that. Usually, these things are designed to use dynamic memory, or JavaScript, and it requires you to simulate or provide these features in the kernel, and that's where it becomes very important to add as in a dynamic way. So power management services, tomorrow there will be actually a session specifically dedicated to power management in Zephyr. So I encourage you to attend that if you have interest there. So basically we have tickless idle support. We advanced idling structure. This is something that you can implement in your application. So basically, if the kernel goes into the idle task, you can instruct it in the application code to actually go into deep sleep and wake up on events or in other means. Yeah. So again, tomorrow there will be a session about that. Highly configurable. We touched on that. All system resources need to be defined at compile time. I mean, this is not really a must, actually, but it's how things started. We actually added some dynamic objects, as we call them. So you can either, and this is the traditional way of doing things, you can define a semaphore or a mutex statically, but you can create those dynamically as well, if needed. Okay, so the one before last year provide minimal runtime error checking, and this is basically, it's not that we are writing bad code here, or we don't check for it. It's a way for us to minimize the footprint by not introducing a lot of overhead there for error checking. There are, however, in the code, if you look at the Zephyr code, there are a lot of ways to do error checking without increasing using asserts, for example, without increasing the footprint. This and other features and other ways of how the kernel is developed really contribute to the small footprint, and having kernels doing useful operations in less than 10K or less than 8K, things that would fit on the smallest of MCUs. The overhead of error checking and other code style, it's something that has to be done, obviously, in a educated way. I mean, it's not checking for errors can be harmful as well. Yeah? So that's something that when we review the code, we always make sure that it is safe in a way, and if there is no error checking, we recommend to use asserts, as said before. So we are a library-based RTOS, kernelless, I said before, so one single executable binary. No loader is required to dynamically load applications at runtime. This actually minimizes the operating system code and also reduces the context switching time because there is no user space to kernel space calls. However, this actually introduces an interesting problem because you don't have multiple rings. You have basically one address space, and my application or the user application can just, it has root access all over the place in this case. Yeah. So this becomes a little bit of a problem, but I mean, on small microcontrollers, on which only one application is executed anyways, that disadvantage here is actually becoming acceptable. Yeah, because you are running your code. Nobody else will actually introduce an application and try to interfere with what you are doing. So the nanokernel is a configuration option that would allow you to run on the smallest of devices, usually like something like a price tag. It's ideal for system with sparse memory, very small. You can build a nanokernel, with only 2 kilobytes of memory consumption. So it is, it is not something you want to use on connected. You can use it on anything in this case because the drivers and the network stack actually would still work with the nanokernel. However, if you are going to go for the nanokernel, then it probably you don't have any services, you don't have any network. Yeah, because if you are going networking and adding additional features, then probably it makes sense to use the microkernel anyways, because it supports multitasking, and it has additional services. So when talking about kernel services, so the nano kernel supports one background task, fibers that are cooperative in this case, and a few kernel services like FIFO, LIFO, stacks, and so on. So it's actually very limited. It's also your interface to the architecture. That's where the context switching happens. If you want to go, and this is basically additional features and the scheduling of the nano kernel. If you want to go actually a little bit more advanced and be, operate in an IoT environment, then it makes sense to use the microkernel directly and use the rich services it provides. So the microkernel is actually a superset of the nano kernel. So it's not like you can have either the microkernel or the nano kernel. So you will have the nano kernel, and on top of that, the microkernel. The microkernel actually is almost an application on top of the nano kernel. Its example here is like fitness wearables, smartwatches, IoT wireless gateways. So actually, it can, depending on the networking capabilities and the protocols you add, you can pretty much do everything with the microkernel. So here, as you can see, there are additional services. So you have memory pools, mailboxes, pipes, events, memory maps, and you have multiple tasks. And this is actually the important thing. So you have a real multitasking environment here that is preemptible and priority-based. And you can also enable round-robin time slicing. And it's mostly used for data processing. So if you have a sensor, you are reading data from a sensor, you want to be able to process it on your device before sending it to the cloud. So if nothing has changed, you don't want to enable or turn on the radio even, So you want to do local processing, see if something has changed, and then if something has changed, then send it to the cloud, and then go to sleep again. And probably do a few other things as well. And that's where multitasking becomes very important. So the last part here, so if you look at Zephyr today, it actually, at first glance, it looks like the Linux kernel when it comes to the tools. So we are using the cable system. We're using kconfig. But that's where it stops. Obviously, we are not trying to create another Linux here. The way these tools are used in Zephyr, it's a little bit different from how it is used in the Linux kernel as well, because of the way our application built. We build one single binary that is basically your application. So it is a little bit different from Linux, But in many ways, I have been a Linux developer for 17, 18 years. So there's some influence there. And most of the people working on this project have this Linux history there. So you will see a lot of things. And also, our release process and how we develop and how we deal with the community, it's inherited from the Linux world. But we are not trying to be Linux. So we're trying to learn from the best. And in this case, Linux is a good place to learn from. So we have an SDK, basically, but that allow you to get started with Zephyr for building for the different architectures and boards. Right now, we have 5 different cross-compilers in there, and the list is growing, actually. So I'm talking here about ARM, x86, an optimized version for Intel MCUs, MIPS, ARC. And we are not reinventing the wheel here. It's just we are just putting everything together in one single binary that can be used to build on Linux in this case. Also support flashing and so on. Obviously, if you have your own favorite cross-compiler installed in your system. Like, for example, if you have the ARM compiler that you can get from Launchpad, you can just download it and use it exactly the same way. It's just a configuration option. So you are not really limited to using that. We build natively on Linux, obviously, Mac OS, and Microsoft Windows as well. And last but not least, there's a project going on right now done by the Yocto team, who is actually supporting us also with the SDK to enable building on basically on all of these OSs using containers, using Docker containers. Basically remove the complexity of installing a native and building on a native environment. On Mac, it's actually not a problem. On Windows, we had to do a lot of changes to make Zephyr build natively on Windows, and that was not fun, if you ask me. I mean, I would really like to see this simplified without having to go through all the hassle of installing Unix tools on Windows. So when it comes to supported platforms, I mean, the project was launched over 1 month ago. We have been working with the partners on adding support for various platforms that are available from them. But on launch, actually, we had these platforms. So the Arduino 101 is a Quark SE based MCU. Yeah, I mean, this is something you can buy from Arduino website, arduino.cc. And it's an interesting device because it has x86, it has ARC on it, so it's basically a dual-core SoC, the Quark SE. One is a sensor subsystem using ARC, which is running Zephyr, or can run Zephyr, and x86, which is the main application processor. And it's you can basically get it and put Zephyr on it and run and do your multi-core processing if you want. There's a communication or an IBC mechanism implemented between the two cores. So it's very interesting platform to start with. It has also Bluetooth support that is actually supported natively in Zephyr, but the firmware on the device makes it a little bit difficult, so we have to wait for an official release of the firmware for the Bluetooth. Quark D2000 is another interesting platform. This is a very small SoC that has 8K of RAM. This board specifically can actually be purchased right now, but I think in the future we will have other boards based on this SoC that will natively run Zephyr. So Zephyr actually runs there, and it's the smallest of devices that we actually support right now. And it's an interesting platform for simple sensor use cases. Galileo has been supported for a while. I mean, it is not really a target system for Zephyr because it can run Linux, but we use it for development. I mean, all the IOs are supported, and we use it for, mostly for development right now. The Freedom board from NXP, it's one of the primary ARM boards we support. We also have support for the Arduino Duo, which is an Atmel board. So you can basically, I mean, at least the Freedom board and the Arduino one are available with the demo or as part of a demo on our booth outside there. Yeah, so you can go and take a look. And we also have another demo using Synopsys evaluation board running Zephyr as well with an accelerometer or 9 degrees of freedom accelerometer. So we have the 3 architectures supported by Zephyr presented there. More boards to follow. This is just the start. We actually, since the launch, we have additional boards and additional vendors supported. So I think 1 week or 2 weeks after we launched the project, We got a lot of interest from STMicro users that actually submitted their code, and right now we have basic support for STMicro, and more support is coming. I know there will be a lot from NXP. There will be a lot of boards from Intel as well. So this is this is hopefully next year like now. This page will be really full. Yeah, I will need more than one page to show the supported platforms. So next steps. So it is an established code. So it's not something that we started from scratch. It has been there for a long while. Obviously, we are making it actually. We are making a lot of changes there to make it open source friendly, yeah, but this is done now. And we are ready actually to make it more attractive with contributions from major partners and also from the community. So it is focused and committed to support industry standards. We don't want to reinvent the wheel. We don't want to duplicate effort. So that's why we are looking at other projects and working with other projects. I know, I started this talk saying that the market is fragmented and there are many OSs. And there are, since the project launched, 2 new RTOSs were announced. Yeah, since February 18th, there are 2 additional projects that were announced. And I think that the trend will continue. And I don't see that as a competition. I see that actually as a good sign. And we want to work with these projects and to make sure that, obviously, people have their own, or there are different companies that have different interests and so on. But when it comes to standards and to protocols, we want to work with the community and with others to avoid duplication, especially when it comes to IB stacks and applications and middleware. We want to be innovative here, and we are innovative and be forward-looking. We don't want to just maintain the status quo and just create something that is available in multiple times by different people. We want to be forward-looking. We want to support new technologies, new protocols, and be the first there. Yeah, and with the industrial support that we have, with the commercial support and the major players involved in the Zephyr project, I think this is something that we can achieve. It is open to all. Everybody's invited to join the project as a individual contributor or as a company. It's basically, this is one of the goals of the project, yeah, to be open for everybody and to have people basically join the ride and make this happen. So go to the Zephyr project. Unfortunately, I think I forgot to put an URL here. Here it is, yeah. So it's zephyrproject.org. The code is available, a lot of documentation, direction, take a look. If you have any questions, we have a booth out there. There's another session about the Zephyr project power management features tomorrow, so make sure you attend that as well. It's very interesting. And yeah, if there are any questions, then go ahead. I think I am right on time, yeah? Go ahead. Can you go? Microphone, yeah.
So you mentioned earlier during your presentation that you can go down to 8 kilobytes with your footprint, with Zephyr footprint. But then, so that will make it possible to port to very small and kind of simple architectures like the MSP430, which is the option or the choice for really small stuff. Yeah. Of course, you can go now to the MSP432 whenever TI has it ready. not today. But then I didn't see anything there. I saw a lot of Intel and, of course, Arduino. But is there any plan in involving either TI, or is there any initiative right now to make the port to the, for example, specifically the MSP 430?
I didn't catch that. It's a little bit difficult to understand. What board or what architecture are you talking about? TI what?
MSP 430.
Oh, MSP 430.
Yes. And along with that question, I thought that I was, shouting. How documented is the process of porting, and how easy it is to port it in case one decides to go and port it beyond the ones?
So regarding the TI MSP 40, you are the first one actually bringing this up. Yeah, I am aware of that, and it's not something that we have on our roadmap, or we haven't seen any interest shown in this MCU or in this architecture. And but the project is open. Yeah. So if you think actually it brings any value, then yeah, we want to discuss that with you, and we can start talking about that. There is no problem there. When it comes to size, however, I mean 8K, when I say 8K, because the small device like Cortex M0 and Cortex M0 Plus actually can go to 8K. And these are like the most popular devices out there. 8K, when I say 8K, this is something that you can comfortably run an application with a real use case. We can actually go down to 2K, but it obviously will just do nothing. Probably will just print hello world, yeah? So MSP 430, definitely interesting if you think this is something that Zephyr should support. Sorry? Yeah, and yeah, I don't know how hard. It depends on the architecture, of course, right? But from a Zephyr perspective, the hardware support or adding a new architecture is something you do on the nano kernel level only. You will get it out. The microkernel is just a superset, yeah? So how hard? Personally, I didn't do any architecture support or addition. It's something, it depends on what features you want to support and how difficult it is actually, originally, how difficult the architecture is, yeah? Yeah, okay, I mean, I'm getting signaled there, yeah, but if you have a question, you can come to me and we can talk directly, yeah? Okay?